So today we have Duncan speaking on an operaad structure for the Goodwillie derivatives of the identity in structured ring spectra.
All right, so just want to say thanks for the invite. It's great to be here. This meeting is being recorded. Great. I just want to preface this talk by saying if there's anything that you want to interrupt and just ask about, please feel free to do so. I'm more than happy to like sort of break pace and chat further about things as we go along. Just because I think some of these topics might not be as commonly understood. Cool. So what I want to talk about is some of my work, which is putting an operaad structure on the Goodwillie derivatives of the identity, specifically the identity functor in structured ring spectra. So things that can be described as algebras over some operaad and spectra. And I want to sort of start with this like sort of main idea, which I'll put in quotes because it's not really shown yet, but it's kind of like a moral that guides this, is that the identity, the derivatives of the identity in a suitable model category. So this guy is just notation for the Goodwillie derivatives. Derivatives of the identity on C, where C is just some nice model category. Basically a model category that's sufficient for doing functor calculus. Should come equipped with an operaad structure. So this might be sort of a, something that seems strange. Like, why would we expect this? Well, some sort of propaganda for this is that back in 2005, Michael Ching showed that you can construct an operaad structure on the derivatives in top. Ching provides an operaad structure. And sort of unraveling his proof, it begins to seem sort of expected that those same techniques should carry over to other model categories. And one sort of nice place to work that sort of feels similar to top is in AlgO. So algebras over some operaad. And this is what I'll be talking about today. So do that thing where you just put your last name. Cool. So let me begin by just giving some overview of functor calculus, because this is, yeah, it's a cool subject, but it sort of takes some time to really piece apart what Goodwillie's writing about sometimes. So let's talk about functor calc. So the main idea is that if you give me a functor between nice model categories. This also works for infinity categories, but I'm just going to do all this in the language of model categories. And by nice, I mean, well, it should be symmetric, monoidal, and the monoidal product should pair nicely with the model structure. It should be pointed, and it should have some understood notion of stabilization. And probably you want your product to be closed as well. So associated to any sort of functor that preserves homotopy, so this guy preserves homotopies, just meaning that, if I have two objects that are homotopic in C, then their output is homotopic in D, then I can always associate to this a Taylor tower. Like so, of n excisive approximations. So such that, say, Pn is n excisive.
So can I ask a quick question?
Yeah, go for it.
When you say preserves homotopy equivalent objects, do you mean like it preserves the weak equivalences of the model structure, or do you mean that?
Yeah.
Okay.
Exactly. Yeah, that's probably a better way of saying it.
Not like actual homotopy.
Yeah, let me write preserves weak equivalences.
Thanks.
Makes me feel better too. So we have these n excisive approximations, and another word for n excisive is like polynomial of degree n. Or I should more technically say degree less than or equal to n, because 2-degree polynomial is also a 3-degree polynomial. And if we want this tower to really mean something, then we might also ask for, for nice f, that I can recover at least up to homotopy the value of f on x from this tower, like so. So for nice F, the keyword is analytic, meaning it satisfies some sort of connectivity properties, sort of like you get from the higher Blakers-Massey theorems. And I'll just say sufficiently connected X. So nice model category, meaning, you know, top, at least for highly enough connected guys, that you'll get this sort of desired equivalence in property 2. Now, when you go to analyze these guys, it turns out that actually analyzing the n-excisive approximations can be rather difficult. But to really get information from this tower, you turn more to these layers. So let's just denote DNF, the homotopy fiber of Pn to Pn minus 1. There's a theorem that this is an n-homogeneous functor. So dn of f is n-homogeneous. Goodwillie proves this in the case of top. And later this is sort of generalized to work in other suitable categories as well. And moreover, an n-homogeneous functor will always be classified as follows. dnf of x is going to be equivalent to the underlying space. I have some spectrum with the sigma n action. So let me preface this by saying in top, DNF will always have this form, where I have some spectrum here. DNF, partial n, is a spectrum with a sigma n action, called the nth derivative. So, at least in some sense, this sequence of derivatives is telling you most of the information that you'd like to know about the functor. So in good cases, you can sort of recover everything that you'd want to understand about f by sort of just understanding what this symmetric sequence of derivatives is and maybe some additional structure on it. And this is work of Aron and Ching. But you know, another reason to maybe call this functor calculus is that if we're thinking of these guys as polynomials of degree n, these PNFs, then DNF looks very similar to like a homogeneous monomial in terms of ordinary calculus. So there's always this analogy where you can think of this as being very similar to the guy that you get in your Taylor series from ordinary calculus. So, you know, I have input smashed n times. I have some number that tells me something about the function, and then I divide by a group with n factorial elements, which might be the loosest analogy of the three. But, okay, let's look at maybe an example. Just to sort of highlight some of these properties. So identity functor in spaces, I don't want to put example there. I want you to go up. So identity in top. All right, so the Taylor tower for the identity in topological spaces is sort of understood by some work of Johnson and then later Aron and Mulholwald. The first one excisive approximation turns out to be equivalent to stabilization. So this map right here, oh, let's put an X in. This map is the map that gives you the comparison from unstable to stable homotopy groups. In particular, this is a one excisive functor, a linear functor, behaves like a homology theory is one way to think about it. But as I go up the tower, these guys become a little bit more mysterious. It's quite difficult to just compute from Goodwillie's definitions what you might expect these excisive approximations to be. But we know from Johnson and later Aron and Mulholwald that the nth derivative of the identity in topological spaces is related to the partition poset complex. So I'll just write this down. It's the pointed mapping space from P of n into S, where this guy denotes the partition poset complex. And this is due to Johnson and Aron and Mulholwald.
S is the sphere spectrum?
Yes. So Partition post-up complex is a simplicial set, and then you just push it into spectra. So in some sense, this tower is well understood, and in particular, it's one analytic. So the identity X will be recovered by this tower for one connected X. So giving some sort of overview of properties that we know about the identity functor in top, because a lot of these will sort of carry over into working in algo. Right. Is there anything else I want to say about this guy? I don't think so. Yeah. Cool.
Can you describe what happens if X is not one connected? Like
That's a good question.
What does this whole limb look like?
So this whole limb will always tell it, this whole limb will be very related to, let me just write, related to the Bausfield-Kahn completion with respect to stabilization. So this is something that's going to come up later in the talk. It's a great question to ask now, but my answer will be sort of sit tight, and then I'll hope that my explanation says more about it as we go.
Thanks.
Yeah, but good point. All right, so we want to sort of tell the same story when we work in the category of algebras over operads. Let me just give a brief crash course in how to sort of deal with these objects, what algebras over an operad mean. So operads and their algebras. So my operads will always be in spectra. Just for concreteness here, you can define operads in a more general setting, but we're going to work with specifically the category of symmetric spectra as defined by Hovey, and Smith. So symmetric spectra. But it shouldn't necessarily be constrained to any particular model. It's just this is what I'm most familiar with. So an operad is a sequence. I got an O of 0, an O of 1, O of 2, etc., along with symmetric group actions, plus associative and unital maps, of the form O at level n, smashed with O at level k1 through kn, down into O of the sum. So we think of operad, we're going to care about them because of their algebras, and we think of the operad as sort of describing the possible n-ary operations. So ON, maybe I'll say describes the n-ary operations allowed by this operad. So for example, I could say, example, let me define algebras first. In an algebra, X is an O algebra if there are maps of the form O of n, x to the n, and then I smash them together over sigma n. O of n comes with a natural symmetric group action. There's a natural symmetric group action on x smash n just by permuting the factors. So I want those two to know something about each other, and they should map down into x. So for example, plus associativity and unitality conditions. And unital. That's not how you spell unital at all. That looks like MTA. It's just going to go away. Unital. So we think of these guys as sort of saying, like, for example, if O of n is just equal to S for all S's, and there's no interesting trivial or no interesting symmetric group actions, then this would give us strictly commutative ring spectra. In that, I have S Coinvariance over sigma n, x to the n. This is just equivalent to take the homotopy orbits over sigma n, and it's basically saying no matter how you choose to arrange these things, you're going to get the same output, and there's only one of them. So it's got to be a commutative operation. So this is the world that we're going to be working in. And let me just scroll through my outline here so I don't miss anything. And by sort of varying this operad, you can describe other sort of interesting homotopical structures that show up. If I sort of lax this to be only equivalent to S plus some freeness condition on the symmetric groups and their actions, then you can reduce this to be, say, homotopy commutative ring spectra. If you sort of relax this condition here, or just describe sort of any sort of algebraic structure that you'd like by finding an appropriate operad to describe this structure. So let me just say operads are monads with respect to a circle product for symmetric sequences called O, meaning that I have maps O, circle O down into O, along with a unit as so. And the unit is just the guy who is the sphere spectrum at level 1 and a point everywhere else. So I won't necessarily say what this composition product is, but a way you can think about it is that operad at level n is sort of like the coefficient to a formal power series. And then this composition product tells you the coefficients of the composition of two formal power series. But it takes into account the fact that those coefficients also have some sort of natural symmetric group actions on them as well. But it defines a monoidal product on symmetric sequences with respect to which operads are monads. Any questions so far? I feel like I should pause maybe more frequently just because it's an online thing. We're going to move into the world of blending these two subjects now. Perfect. So let's call this next part functor calculus and algeo. That's pretty apt. So if you go back and think, what do we need to describe functor calculus? Well, if I look all the way back up here, yeah.
You mentioned a quick sentence about like operads and like polynomials or something, and it was interesting, but can you just repeat that sentence?
Yeah, it's about the composition product. So this guy down here, and then I'll go back up to where I was. Green is like a comment. So this circle product, also known as composition product, sort of looks like composing formal power series.
Okay.
Formal power series.
Uh-huh.
So this can be kind of a difficult product to work with just because it's not, it's just cumbersome. But sort of a good way to ground yourself is to think, well, I'm sort of modeling this off of what does it mean to compose power series, where the coefficients have some like extra structure with the symmetric group actions.
Okay. Thanks.
Cool. Yep.
Thank you.
When you say operad structure on the derivatives of the identity, do you mean
Yes.
those are like the spaces of the operad or the spectra of the operad?
Yes. So I mean that, the Goodwillie derivatives, let me go back up here because I'm going to be up here anyway. These Goodwillie derivatives, they assemble into a symmetric sequence, d star of f, where the nth entry is the nth derivative. It comes with a symmetric group action. And that's sort of the input that you would say an operad is this structure, this thing, plus being a monad. So the tricky part is showing, like, does it have these sort of composition maps that we'd expect? Like, for example, is there a D2 of I / D3 and say D4 mapping into D7? So like, how do you construct these maps?
Okay, thanks.
Yeah. It's a good question. This is all just kind of like tricky, I think. It took me a while to really, I guess, get everything that's going on here. Right, so one thing that sort of underlies what we are doing when we're looking at functor calculus is that there's always sort of stabilization coming into play. It's the two are hand in hand, like they love each other. Functor calculus is really giving you some sort of filtered interpretation between like a category and its stabilization. So if we're looking to describe functor calculus in AlgO, maybe a good place to start is how to understand stabilization. Stabilization. For the longest time, I was spelling this with an A here, and that's just not a word. Nor is stabilization if you look in the dictionary, but it's even less of a word if you put an A. Anyway, so understand stabilization of AlgO. All right, so this is sort of step one. Well, I'm going to fix an operad, and we'll just work with this operad for the rest of this talk. And for sort of technical reasons, I'm always going to think about operads with O of 0 being a point. You can generalize this a little bit, but we think of these guys as giving us non-unital things as their algebras, and they're just easier to work with. And I'm also going to consider those guys where O of 1 is the unit. This part is not required, but it really simplifies what I'm about to say. So I'm just going to work in this case right here. This guy isn't even, this is saying that my algebraic structure, I can't sort of, I have no interesting one-area operations. The only thing I can do to X that fits into the operatic algebra on it is just leave it as it is. All right. Now, associated to such an operad, we have sort of a sequence of truncations. So I'll define this nth truncation, tau n o at level k, just to be the guy you get by killing off all the higher area operations. So if k is less than n, less than or equal to, it's the same thing, and it's a point if k is too big. So this gives us a natural sort of filtration of our operad, where I have O mapping into tau 1 of O. There's a map down just by collapsing the higher level gadgets. These are all pointed. AlgO is a pointed model category. That's another reason that you need this. This makes it pointed. Forgot about that earlier. And you go up. So we have a tower. And associated to any, I should say, tower of operads, meaning each of these guys is itself an operad that knows a little bit more about O as you go up the tower. So associated to any map of operads, we're always going to have a change of operads adjunction. But I'll sort of start by saying, it's like, this guy here will give us a change of operads adjunction. But before I write that, let me just say, like, for example, if I have R to S, a map of rings, and in the true homotopy fashion, I mean ring in the ring sense, not like the spectral ring, then I get a change of, an adjunction between the category of modules by saying, if I take an R module, well, I can tensor over R with S on the left, and then I can sort of forget along this map. Change of operads adjunction is exactly this idea. I look at this bottom map of operads, O into tau 1 of O, and I get a comparison between algebras over O and algebras over tau 1 of O. This guy is just obtained by saying, this guy has an O action, so why don't I take that O action and use the map and sort of do the exact same thing, and there's a forgetful functor. Turns out, if you're an algebra over an operad concentrated at level 1, you are just a module over that ring spectrum that lives at level 1. And what's remarkable about this adjunction is that Bastera-Mandel show, or maybe just Bastera, but it's in several papers of Bastera and Bastera-Mandel, that this is equivalent to the stabilization adjunction, where by stabilization of aljo, I mean, aljo is pointed and it has or more specifically, it has a simplicial tensoring, so I can define Bauswald-Friedlander spectra that might seem impossible to work with, but actually Bauswald-Friedlander spectra are just the same thing as modules over O of 1 when I look in aljo. So this is a change of operads adjunction. I'll just say a warning, and I won't necessarily say anything more about this because I don't want to say too much about sort of model structure theoretic things. But what we're really going to do is say take O, factor it as a cofibration followed by a weak equivalence into this guy J, where J algebras are the same as tau 1 algebras, and refer to this adjunction Q and U as stabilization. This is our definition of stabilization. So the QU adjunction is equivalent to sigma infinity loops infinity for O algebras. And of course, Q is given by J circle over O with blank, and U is forgetful functor along that map of operads there. The reason that, yeah, go ahead.
Just to, am I making a mistake? Because if you have the like tau 1 of O, right? Algebras for tau 1 of O, it seems like they should just be that like spectra, right?
Yes, yes. With this extra condition here that O of 1 is S, mod O of 1 is just S modules. It's just spectra.
So like you can like recover the category in which your operad is acting in this way.
Exactly. Yeah. It's basically saying, stabilization looks a lot like forget about every more than one array operation and just look at things of that type.
So like stabilization of like rings would be like, I mean, or ring spectra would be just like spectra, or yeah, would be just spectra.
If you work with like strict ring spectra, then yeah.
And the other thing is, so I'm getting the impression that you have some model structure on operads.
This is possible. It's a little tricky to define. Aron and Ching give a description. It's cofibrantly generated by certain types of free gadgets, but it's just kind of combinatorially nasty to like present.
So then, do we in this model structure, do we have that this tower of operads is actually a Goodwillie tower for the identity on operads?
It's possible. I mean, I wouldn't be surprised if it is. That's kind of going, I think, a step higher in hierarchy than what I'm looking at here, but that's a reasonable question to ask.
Okay, thanks.
Yeah. So it is now 1:30, and as seems to be standard in this talk, I'd like to give a picture of my cat. This is the very desk where I'm sitting right now, and this is him being fluffy. So that's Leo. And you can see me taking a picture of him because apparently I'm also in Zoom at the time. Anyway, let's get back to math. So we have our understanding of what it means to stabilize an O algebra. Let me zoom up here. And in particular, this left functor, this Q, the guy's stabilization, Q, you can always compute, well, let's define its left-derived functor to be TQ. So this is what is commonly referred to as TQ homology, topological equivalent homology. And you can compute TQ of an O algebra X via simplicial bar construction. Bar JOX, and this just looks like the derived composition product. It's a model for the derived composition product. So TQ homology, topological equivalent homology, maybe you're thinking about Andre equivalent homology for rings. In fact, the two are very similar. This is sort of obtained as like a spectral operad analog to good old Andre equivalent homology for rings. So let me keep that right there. And now let's focus on the identity in algo. So Harper-Hess and also Pereira, Harper-Hess and Pereira describe the identity. Harper-Hess are looking more at sort of this idea of homotopy completion, and then Pereira comes in and defines really how to construct Goodwillie towers in Alg O. But nonetheless, it takes the following form. We have the identity functor, and then I start with stabilization. And as I go up the tower, I just allow more of the operad on the left. And so. And one way to think about this, because maybe this tower just looks like, all right, what's going on with this thing? Well, tau 1 of O, it kills off all the 2-area and higher operations. So this gadget right here kind of looks like x mod x squared. Tau 2 kills off everything above level 3. Any composite of 3 or more things is gone. So this looks like x mod x cubed, and so on as I go up the tower. It looks a lot like the good old x addict completion tower that you'd get if you had x commutative non-unital ring. And you might ask, in what sense does x converge to the limit of this tower? This is really how Harper-Hess started to think about this in terms of what does it mean to homotopically complete a ring over some nice algebra, over some operad. But let's say, in particular, if I want to look at dn of the identity here, well, Harper-Hess showed that it has the following form. It's always going to be equivalent to U, and then the nth part of the operad sits right there, and then TQ homology goes here. So this is Harper-Hess. In particular, the nth derivative of the identity in Alg O is just weakly equivalent to O of n, which is even sort of more propaganda, right? We had Ching's result that said in top that this guy on the left here is an operad. The construction sort of says, well, maybe this should actually be working more generally. And then we have a computation that says, actually, the spectrum over here is just equivalent to O of n, which is already an operad. So it's very natural to think, can I put an operad structure here that recovers that on O, which agrees with O? So maybe a dumb way to do that is just say, oh, well, it's the same. But what we're kind of looking for here is like an intrinsic structure on the derivatives that can specifically be transported to sort of work in other suitable categories as well. And that's exactly what I show. So this was a long-standing conjecture for a while. It's written, at least in the intro to Aron and Ching's 2011 paper. And if there's time, I would like to say about some implications of what it means that this sequence of derivatives just gives you back O as its operad. It's really reflecting something nice about the category of O algebras that you can then later say, well, if I start with a different category C, can I describe some sort of descent properties where I look at a nice part of C and then pick out something that looks like the category of algebras over this operad of the derivatives of the identity. All right, so let me write my theorem. D star identity Alg O is a homotopy coherent operad. Moreover, it agrees with O. I hope that second statement is clear. So I threw a new word at you here, homotopy coherent operad. I won't necessarily describe what I mean by this. It's not necessarily a new thing, right? Like Lurie describes infinity operads. There's other models for sort of operads where you allow some coherence in the composition product. But what I mean by this is that it's sort of an A infinity pairing, monoidal pairing, with respect to composition product. Oh, so remember, an operad is a strict monoid with respect to this composition product, and sort of an artifact of my proof technique is that you only get this monoid structure up to some higher choice of homotopy coherence. And before I give this proof, I'd like to sort of sketch sort of a simpler argument that sort of suggests why you can only really get a infinity structure via this kind of argument. So I'll put this one in red because I like colors. So an example, this result of, who are they? McClure and Smith show that if X with a bullet in cosimplicial objects of top is a monoid with respect to the box product, then hit it with tote and you get an A infinity monoid. So what is this box product? I won't describe it, but I'll just sort of tell you that it's a product structure for cosimplicial objects that sort of comes from the product you get on cochains to induce the cut product pairing. In fact, it'll give you the same thing if you used old con, but this is basically kind of what that's doing. It's like using the idea that, well, cochains have a cut product pairing, cosimplicial objects have a box product pairing with respect to some nice structures. But for example, one thing that they show is, well, if I look at loops on X, this is certainly an infinity monoid. It's homotopy coherent multiplication is given by a composition of loops, but we only can compose loops in certain ways, and there's homotopies between those compositions. So this guy is equivalent to tote C of X as A infinity monoids, where this C of X looks like the Kobar construction point X point. So what I mean by that is I have a point, I can include the point at the base point in X, I have 3 maps up, the outside maps include the base point, and the inside map is induced by the diagonal. So D1 is the diagonal, and so on. So it's kind of a fun exercise. The pairing here is induced by the natural isos that just say, if you give me X tensor or cross P cross X cross Q, this is just equivalent to X cross P plus Q. This induces a box product pairing. And then what you get out is that, oh, well, actually, tote of this Kobar resolution is equivalent to the loop space on X. And moreover, the A infinity monoid structure that you get is equivalent to the A infinity monoid structure on loops of X. So this sort of underlying idea that I take something I want to understand. So start with this guy, look at some resolution, meaning this Kobar resolution, and then try to induce the structural pairing on the Kobar resolution to sort of get this structure, is exactly what's going on in the proof of my theorem here. So I guess I should put my initial. All right, I have 10 minutes. I'm going to just sort of sketch what's going on in this proof because I don't want to necessarily take too long with this. And time permitting, I would like to say maybe a couple applications, even if I just get to them in words. Before I start that, are there any questions at this moment? All right, we will boldly blaze ahead. Let's go back to purple. So proof. Well, remember from this sort of example right here, we're looking for a resolution. So the resolution that we get is the Bausfield-Kahn cosimplicial resolution with respect to stabilization for O algebras. And just in the back of your mind, something to think, oh, there's a rainbow color. That's super cool. Look at that. Is that you can do this equally well in top. And this sort of motivating idea is by Aron and Rinta, which I hope I don't run out of space. So that's kind of where I stole this idea from because it's a super cool idea. So you start with the identity functor. Bausfield-Kahn cosimplicial resolution says associated to that adjunction, QU, I can always build a cosimplicial object like so. The co-face maps are induced by just saying, well, I have identity into UQ, so I can stick that on the inside or the outside, and then I could stick it in between any of these things here. And the codegeneracy maps are sort of induced by a comoanid structure on QU, but it turns out that like you can just work with restricted guys, and we don't even have to really worry about codegeneracies. It's enough just to worry about co-face maps. So I won't say anything more there. Now, this is giving me a resolution of the identity functor. Idea or a result of Blomqvist is that the identity functor on X mapping into holim, first of all, let's call this thing C of X. It's maybe overused, but whatever. Mapping into holim less than or equal to n minus 1, more on that in a second, is K, oh, I'm an eraser still. K plus 1 times n plus 1 connected. So what I mean with K is X is K connected. So if I start with a K connected O algebra, this comparison map, holim over delta n minus 1 just means go up to the n minus 1 simplices and then chop it off. So, you know, delta less than or equal to 2 means, well, I've gone up to here. And then I just look at this restricted diagram up to there. But it turns out that these estimates are exactly what you need in order to conclude that the nth derivative can be recovered. And this is where I'm just going to start sweeping a lot of details under the rug, be recovered by the derivatives of the constituent pieces. So in particular, this tells me that if I hit this guy with Pn, then I get an equivalence, this polynomial approximation. As a corollary, I can recover this thing down here. So I get a cosimplicial resolution of the derivatives of the identity via the derivatives of sort of composites of stabilization. And now, well, we've sort of transferred one problem into another. Is it possible to better understand these guys?
Sorry, should that be should those be d sub n's?
Yes, because this is an n. Thank you. N. So I might just write star at some point. Just it means level-wise. Everything's just computed level-wise. Better understand these? Question mark. Well, the answer turns out to be yes. So one way to understand this, and this is kind of the idea behind this Aron-Kahn-Rita paper, is that you can use the Snaith splitting. So let me say first, Snaith splitting. This is sort of a classic result that says in top that if I look at suspension spectrum of stabilization of a space, that this will split in terms of, I might be writing this atypically for if you've seen this splitting before, but really the Snaith splitting, I don't want an eraser, says that I have a splitting like so, where the sigma k action here is trivial. Snaith splitting tells me that I have a strong splitting of the co-unit, that I know all of its Goodwillie derivatives, and moreover, that it's just the coproduct of the homogeneous layers, which is a pretty strong statement to ask. Turns out, you get the same thing in aljo. If I look at the co-unit applied to, let's say, a spectrum, because that's what the stabilization is, then what I get is equivalent to, that's an ugly coproduct, but we're sticking with it, this guy. BO of k smashed over sigma k, y to the sigma k. So what this guy here is it's the bar construction on O and then evaluated at level k. Now, if you're familiar at all with this theory, you might be saying, well, this is just a co-operand right here. And the answer is morally yes, but it's very tricky to work with. So we can actually do everything without ever needing to know that this B of O is a co-operand. But it's pretty much a co-operand. So how do I use this splitting? Well, what we're looking at with these derivatives, turns out that I can always, up to homotopy, replace this by identity and spectra. I can just cancel out the first u and the last q. This should be dn of qu. Cancel out those guys. This should be dn of qu. And it turns out that I can then compute dn of, let's write it as follows. U, qu to the k, q. This would be the kth level of my cosimplicial resolution, is equivalent to dn of qu to the k, is equivalent to b of o circle k at level n. And via some long-winded string of equivalences, this just turns out to be j circled over o, where there is k plus 1 j's at level n. So again, sweeping a lot of details under the rug, the result is that C of, the cosimplicial model for the derivatives that I use is as follows. dn of the identity, we just take to be equal to tot of C of O at level n. And this is really tot restricted, but ignore that for now. Where C of O is the cosimplicial diagram, that is J, just J, into J, circle over O with J, J, circle over O as follows. Where the coface maps are induced by saying, well, the D1 map here would be like J, circle over O. I can stick an O, circle over O. It's just equivalent, that's isomorphism, and then send O down to J. So define as follows. This is our model that we're going to use. And I guess I'll finish with this last sort of list of claims, which I can say more about if anyone is interested in. So dn, right. With respect to this, with respect to, I don't want to write that. I want to write the following. One, C of O is a box monoid, where now this box is with respect to the circle product. As it turns out, if you know much about the circle product, it's not a very good product to work with. It doesn't actually commute with co-limits in both variables. This turns out to be kind of an issue, but in the end, I still get what I want. You just have to relax this to say it's an oplax monoid, which is an ugly term, but it basically means that you can only sort of define the n-fold part, and then you have sort of partition maps that say, if you wanted n things to be multiplied this way, you have a map in that direction. And two, that with respect to this oplax monoidal structure, that tot of C of O is an A infinity monoid with respect to the composition product. So this kind of just pops out. It turns out to be rather difficult to describe this A infinity monoidal structure with respect to the composition product. What I end up doing is defining a certain category of n-colored operads with levels. There's descriptions that are known of n-colored operads whose algebras are operads. So colored operads are like a hierarchy above. They sort of have different colors that can help you describe different structures. In particular, you can describe operads as algebras over this larger gadget called an n-colored operad. And I found sort of a natural way to describe this n-colored operad in a way that you can then sort of fatten it up. So this is analogous to taking, a strict monoid and fattening it up via an operad to an A infinity monoid. So this ends up being kind of tricky. But it does end up working. And third, well, this is sort of half the battle, right? It was put an operad structure on these derivatives, but also, what does that tell you about the operad structure on O? Well, if I look at this C of O up here, then this came with a natural co-augmentation. I have a map O down to J that gives me a co-augmentation. 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 And the co-augmentation O into C of O, I'll just say induces an equivalence of homotopy coherent operads between O and the derivatives of the identity in alg O. Okay, I guess there's still time for comments or for questions, so let me just finish by saying just a few things about what this number 3 gives you here, because I think that it's kind of, it seems like, well, they should be the same and you prove they are the same. But really, if you start thinking about this in maybe a more general setting, this number 3 says that, alg O is morally going to be the same as alg d star of the identity over O, except it's not, maybe not exactly entirely true by this construction, because when we work with functor calculus, we're kind of implicitly restricting to like connected guys. And I'd like to say something more about the comparison between if I start with a category C and know that d star of the identity on C is an operad, what does this tell me about the relation between some nice part of C and algebras over d star of the identity on C? So this would sort of tell you something about, what part of C do these algebras over the derivatives of the identity recover? And I mean, this I don't know. So this, everything below this line is I'm going to say like speculation line. Maybe this is less speculative, but this is more speculative. And maybe the key word that should go in here is nilpotent. This sort of fits into work of Francis Gatesgory, and then also sort of what Behrens and Resk have been working on with their VN periodic stuff. There's like a nice survey paper of this that's in the handbook. I should say one more thing. I think I've said that 3 times now, so please forgive me. But you can also use this box product pairing to sort of get chain rule. So I'll just put that here. Similar techniques give you a chain rule for functors of structured ring spectra, meaning a way of comparing d star of F and d star of G to the composite d star F circle G. So this is lining up with work of Aron Ching, where they give a chain rule for functors of on top. Yeah, so the results of this type sort of tell you that derivatives of certain functors aren't just random symmetric sequences. They actually have some extra structure of sort of bimodules over operad, the derivatives of the identity in their respective target and source categories. Anyway, I will stop it there. Thank you for listening.
So on behalf of everyone, I'd like to thank Duncan. I also did have a question.
Yeah,
what are the implications of having this operad structure? Like what are applications?
Right, so I guess like 2 sort of things that are like the 2 ones that come to my mind are the 2 things that I sort of outlined here.
Right.
You can sort of gather descent information over C. So something that is interesting that I'm still trying to really figure out is that if I let C be the category of spaces, how much does this guy know about algebras over the identity in spaces top? So it turns out that this operad is equivalent to what is basically the spectral Lie operad. So they're both causal dual to the co-commutative co-operad. And if you go back to like chain complexes, then the Lie operad is causal dual to commutative co-operad. And I think Kuhn has a way of going this way, where he says, you give me a space and I can output a spectral Lie algebra. But something that is interesting to me is sort of how much of top is equivalent to spectral Lie algebras, like how much do these things see about each other? And then another thing you can do is this chain rule idea, which helps you sort of say, if I know that I have a symmetric sequence with this extra structure, then in some sense you can rebuild the Taylor tower and try to better understand something about the functor that you started with.
Cool.
Yeah, those are good questions.
Hey, Duncan. Oh, sorry. Was someone else about to say something?
You can virtually arm wrestle.
I'll just go ahead.
Okay.
So here's kind of like a generic, a random question I've been like sort of a little bit, or I've wanted an answer to for a while. Like, so let's suppose I have, I don't know, let's suppose I have some convergent tower of functors, right?
Mm-hmm.
And they, like, this thing is a good approximation of something I'm actually interested in studying.
Mm-hmm.
What do I need to know about, and let's say I hit this tower with just like the Goodwillie derivative, like let's just say take the Goodwillie derivative of all the terms in this tower.
Mm-hmm.
What must be true for this tower to converge to the Goodwillie derivative of like the limit of the original tower I started with?
I mean, that's a good question. I don't know if I know off the top of my head. I mean, one thing that probably would certainly work is if you knew like these strong connectivity results that tell you that, in fact, you had the Goodwillie tower itself. You know, because eventually then your nth derivative would just stop, and then above that it would just be trivial. But more generally, I don't know. I'd have to think about it a little bit.
Yeah, because I don't know. Or in a couple of examples I'm interested in, I've like found myself in a situation where I have a good understanding of the derivative of all of these terms, but then there's some.
Yeah, I mean, I'd be happy to chat with you sometime about it. That sounds pretty cool.
Yeah, sure.
Yeah, shoot me an email.
Yeah, definitely.
Cool.
I had a question about your Kobar resolution.
Yes.
And like your Snaith's theorem.
Yes.
Thing. So like I'm interested in higher vector bundles. I'm just wondering whether or not like this has any implications for so it's like Snaith's theorem says that if you take the sphere spectrum, if you take like suspension, the sigma infinity of BU1, then and you invert the bot element, you get KU. And for higher vector bundles, there is this thing about like if you take sigma infinity of a KZ3 and you invert like an analogous bot class, then you should get forgot what might have been the K3 or KU. But like, do you think that maybe that could come out of like
out of like a Snaith splitting kind of result?
Yeah, or like looking at the like looking at some Goodwillie calculus of some sort and like seeing like what is transported between.
I mean, that sounds completely reasonable to me. I don't know if I'm the guy to really ask about higher vector bundles. I can sort of say that my interpretation of the Snaith splitting in this context at least seems to be going against the grain of what I've had like two people otherwise tell me their interpretation of the Snaith splitting is. But I think that just might underlie the fact that it's kind of a deep thing. So I just think of the Snaith splitting as sort of telling me that if I have a stabilization adjunction, so let's just say I have C and spectra on C, and we'll just call this, I don't know, S and U. That's probably a bad notation, but whatever. Then the Snaith splitting to me would say something about if you start with a nice Y and you hit it with the co-unit, that you should get some sort of strong splitting. And moreover, that from a Goodwillie calculus perspective, this splitting will be in terms of the kth derivatives of SU, and then y smashed k mod that guy. So I think in Lurie's work, at some point or another, it might be a conjecture, he might actually show it, I'm not actually sure, but he shows that if you have a nice notion of stabilization, that the derivatives of, that's not what I want at all. This thing has a little button that erases, and sometimes I hit it, and then it just like, all bets are off at that point. So the derivatives of the co-unit from stabilization should be a co-operad. But if you're just looking at some sort of strong splitting result, it seems likely that you should be able to get a lot out of this. So I don't know if that really answered your question or anything, but
I mean, no, thanks a lot. I mean, I was just looking for more perspective.
Cool, yeah.
Ari, I don't know if this is at all related to what you're thinking about, but there's a somewhat recent preprint by Chatham Han Yuan on like Snaith type constructions and like orientations and stuff like that, which might be something to look at.
Yeah.
Just came to mind.
Wait, what is this by Hood?
Yeah, Chatham Han Yuan.
Yeah. I've been wanting to take a look at that paper for a while. Yeah.
Any other questions for Duncan?